Good afternoon. Does, does everyone know what a functor is? Is that a yes or a no? Okay, good. Um, and um, now, oh, okay. We're going to get a camera, okay, but we're for the blackboard. No. Good morning, good afternoon. Okay, so well, I didn't invent functors, right? And by the way, one of the mysteries about categories is that they're not sets, okay? But they might as well be. I mean, for practical purposes, we could restrict to a subset, if you like, of the class, which is the category, makes up the category. But then we don't really have to. We don't really have to. But if you do, if you think of a category as a set, then you have maps between the objects, and the objects are just points in the general approach. They're just sort of points, and then the arrows, every arrow goes between 2 points. And you can compose 2 arrows if the point, if the head of the first one, the point at the head of the first one coincides with the point at the tail of the second one. And then you have associativity. So it's a bit like a semigroup. If it were you can. So, by the way, there's something which generalizes the notion of group, semigroup or group. It's called a groupoid. But we won't be talking especially about groupoids, but the definition of a groupoid is quite simple. It's a category which is a set, okay? And furthermore, for every arrow, there's an arrow going in the opposite direction, which is deserves to be called the inverse. If you go forwards and backwards, you get the identity arrow. And objects, they can be identified with identity arrows. I mean, which arrows which are equal to their square, and one. If you have any arrow, then there's an identity arrow which acts on the left as the identity, and then there's another arrow that acts on the right, on the codomain, the range side, as the identity. Okay, but and so if you go forwards and backwards and get the identity, and you go backwards and forwards and get the identity, such inverse arrows always exist. Then it's called a groupoid. And it's quite important to look at some maps. Well, in that case, it's a map is just called a homomorphism. It preserves the product operation. And in general, if you have a map between 2 categories, if it's a functor, that just means that's just the same as saying it's a homomorphism, preserves products. Okay, so you have 2 arrows in the given category, then the domain category, and then you look at the image of the 2 images of the 2 arrows in the second category. Well, then if the first arrow goes into the first arrow, the second arrow goes into the second arrow, then if the first 2 arrows are composable, if they match, then it should be true for the images, okay? And then the product goes into the product. That's I guess that's not too much of a stretch of the imagination to call a homomorphism, right? Okay. And maybe the only reason it's not called a homomorphism is that it's not assumed that the category is a set. But that's in our case, we might as well, we can always reduce to the case that it's a set. Look at this suitable subset. Okay, and but this is standard, what you might call naive category theory, but it's very helpful because I like to build on top of it the notion that I called the classification category. Sorry, the classifying category and a classification functor. Okay, so what do you suppose a classification functor is? Anyone want to throw their hat in the ring? Yes. Remind me of your name, please. Sorry? Yes. Yeah, right. You're Vincent. And what's a okay? So roughly speaking, pretty accurately, a functor is a homomorphism between the two categories. And what makes it a classification functor? By the way, let me just review. If you have a homomorphism between two categories, it makes sense for an arrow upstairs to be an isomorphism, right? If you have an arrow, we discussed that. If you have something going backwards and forwards, and you get forwards and backwards, and you get the identities either end, and that's defined to be an isomorphism. Okay. Well, a functor will take, so any functor will take identity maps into identity maps. That's part of it. But then it'll take an isomorphism into an isomorphism, right? The forwards map will go into a forwards map, and backwards to a backwards. And so isomorphisms go into isomorphism. So isomorphic, if you have isomorphic objects upstairs, then the images downstairs will be isomorphic, right? Okay, so what's so Vincent, what's the classification category? And it's a classification function. I call it the classifying category. So this would be the if this is a classification functor, then this would be the classifying category. Okay, you're being very special. Okay, I'm not talking about algebras. I'm just talking about abstract categories. But you got the right idea. An example of a class, in fact, a good answer to the question. What's an example of a classification functor? Clarissa? But Vincent just said what an example was, I think. Elon? So what's an example of, just speaking roughly, what's an example of a classification functor? And what was Vincent suggesting? Sort of slipped out. We weren't talking about algebras. We weren't talking about C-star algebras, right? But he said something. What did he say, Justin? Yeah, the word K0 slipped out, right? Well, this is very good because that's exactly what I'm talking about, okay? That's an example in a certain context. Yes, Charlie? If you have a commutative C-star algebra, then the top of the spectrum would be a classification function. Is that what you said?
If you want to talk about space and
fundamentally? No, because well, for very special classes of topological space, very special classes, then, but that's a good example. If it's special enough that it determines the space, then going if it is a functor going from the you have to check it's a functor, right? But I suppose maybe it is. Okay. So yeah, so for very special spaces, yes. And please remind me of your name. Oh, Susanna. Okay, well, we were just corresponding, yeah. Okay, good. But and what were you going to say?
With a general classification category, just the things that represent the estimates in the classes of the individual category.
Well, that's a bit of a mouthful. Roughly speaking, if you have this category on the left, which you want to classify, And if it's true that this is a classification functor, then this is called the classifying category. But we have to elucidate, we have to get it straight what it means to be a classification functor. But Vincent, were you going to finish what you were saying? But anyway, you made a big contribution by saying in a certain context, K0 is a classification functor. And one context is UHF algebras. Okay, and even what I started to call stabilized UHF algebras last time. You tensor it with the compact operator. Now that's a C-star algebra construction. If you want to look at just the algebra construction, because for UHF algebras we're not bothering about them. We don't need to bother about the C-star algebra structure. But then this tensoring with the compacts can be done in a purely algebraic way in terms of matrices. So you take any algebra, then you have finite matrices over the algebra, okay? But if it's infinite matrices, suppose it's infinite matrices, then you just look at the union of all the finite, you just look at all the finite matrices sitting in the upper left-hand corner with zeros everywhere else, okay? You can call it the free-flowing, it's just the algebra itself is sitting freely in all the entries of the matrix, of the infinite matrix, except that only finitely many are non-zero at a given time. But then you can multiply those, add them and multiply them in the just like finite matrices, and that's called the stabilized algebra. Okay, and for the stabilized UHF algebras, so for the so last time I let the cat out of the bag, the map to the supernatural number is, if you look at the corresponding subgroup of the rational numbers containing the number 1, then that's the K0 group, and identified in such a way that the number 1 is the class of the unit, or it's the class of the canonical singly generated free module, the algebra itself. So in the unital case, that's the invariant. And in the case where you just have the free floating matrices, infinite matrices, there's no unit, okay? There's no unit because you can't keep track of the entries. You just got the algebra of matrices, but you still have the K0 group, and that will be isomorphic to what it is for the algebra you started with, okay? That's an exercise. Just look at this algebra of the entries in the upper left, very simple upper left-hand corner. And the K0 group of that would be the same as the K0 group of the whole thing. But now the class of the unit, you have to keep, you don't keep track of that anymore. You just have a group. Well, that's for these stabilized UHF algebras, the infinite free-floating algebra with entries in the UHF algebra. The K0 group is a classification functor still. Okay, but now you can't say equals for two values, for two of the groups. You can't say equals because they're just abstract groups. You can say they're isomorphic. Now, for the the unital UHF algebra, you can talk about the abstract groups with the special element, but then that's just a subgroup of the Q containing the number 1. And if two of those and if two of those things are isomorphic in a way of preserving the number 1, then they're equal. Okay, so that's but in both cases you get the classification function. So for the UHF algebras, for the UHF, and then for the free floating one based on UHF. And so let's formulate carefully what it means in terms of the diagrams, of the schematic diagrams. So any functor takes isomorphism upstairs, takes an isomorphism to an isomorphism. Okay, but what do we require? What do we actually require in addition to call it a special kind of function, classification functor? Charlie, were you going to say something about that?
To the representatives of the classification have
Well, I can't quite, they're sort of unique anyway. This is a map, right? If these are sets, then this is just a function, okay? And so every object here goes to an object here. Every map goes to a map between the appropriate objects. That's what a functor does. But so I didn't quite catch what you were saying. Free sheep, you want to comment? I mean, it's a, you know, there's a difference between if you say something which is half right. It's hard to tell whether it's 90% right actually, or only 40% right. Okay, and I think that I'll give you the optimistic interpretation. Okay, Charlie. In fact, yeah, but no, of course, we're just talking. But do you want to follow up on what you said? Well, okay, but remember, we're interested in when two objects upstairs are isomorphic, right? And if certainly, for any functor, if they're isomorphic upstairs, they're isomorphic downstairs. Yes, I think I can see the light bulb. Even if it's banned, even if it's banned.
You have two objects that aren't isomorphic in the original category.
Okay, but no, don't always avoid contrapositive. Say something in a direct way. If they are isomorphic downstairs, then what? Okay, so Rishi, I know you know it because we might have touched on it in the past when you were doing the special what was it called? Anyway, it was a summer. It was during the summer, right? A year ago, and it was no. But anyway, we talked about all kinds of things. But yes. Now I forgot. Ask them. Who's them?
Yeah.
All right.
Two things are isomorphic.
Well, no, that's what's automatic. Okay, but now I was too brittle. I mean, I jumped on Charlie when he was going to say the correct thing, and I just said you should say it the opposite way. Okay, which is instead of saying so P what
Two things that are matched to the same thing in the classification. It can only get isomorphic.
well, all right. Well, that's kind of cheating. Okay, I mean, but I was hoping you'd say this. Just suppose that they are isomorphic, and I separate out the two implications. Like that's the clearest way. Okay. Well, I mean. So, well, I'm just being silly, but so what you're coming down on is if they're isomorphic, the two objects upstairs, without any map between them a priori, if they're isomorphic downstairs, then in fact there's some isomorphism upstairs. Now we don't even require that the isomorphism is supposed to give you this isomorphism by the functor, okay? If that happens, and that's usually what you prove when you prove it. That's usually what you prove, and then you could call it a strong classification functor. And that's and it's slightly tricky because we're just saying isomorphic upstairs, then they're isomorphic downstairs. Well, you were going to say if and only if, but I think it's better to separate. It's clearer to separate because one is completely automatic, and the other is highly special. And I'd like to get credit for calling it a classification function. Because if it's UHF, then if it's unital UHF, then you don't really have to use that language, okay? Because it's just if you like, it's the range of the trace, the unique normalized trace on idempotent. That's a bunch of numbers between 0 and 1, rational numbers, and you look at where that's the intersection of a group of rational numbers with the interval 0, 1, which is the K0 group. But so, but it's just a computation. You're not talking about anything being isomorphic. You don't say two groups of rational numbers containing the number 1, two subgroups of Q containing integers. It's not important that they're isomorphic. What's important is they're equal. But in the well, if you go past from the UHF to the free floating matrix algebra, then the you can say that you still have the K0 functor, and you can say that you compute it by just looking at the upper left-hand corner, because that is an isomorphism, but it's not an actual isomorphism. You're not entitled to keep track of this except for computational purposes. But when you're finished, you just have a concrete group which is isomorphic to the, so the best you can say, if you have two UHF algebras which are stabilized, and you look at the corresponding K0 groups, the most you can say is, are they isomorphic? Not equal. And if they're isomorphic, then it's true. Dijkstra was able to prove. This is a good exercise, okay? This is one of today's exercises. Prove K0 is a classification function for the free floating matrix algebra. Over UHF algebra. And by the UHF algebra, I mean the algebraic, infinite algebraic tensor product. Okay, so that's a very good exercise. Of course, it's taking for granted that in the unital case, where you take the you want to know that if you have the K0 and then the class of the unit, then this is a subgroup. It's a subgroup containing the integers. It's in a very natural way. It's a subgroup, actually a subgroup of the rational numbers, okay? And this should be a functor with regard to homomorphisms, unital homomorphisms here. And what is it? Well, it captures the supernatural numbers, okay? So I'll write my own little essay on an email outlining what this essay project is. Okay, I think it's a very good essay project to work with the unital UHF algebra defined as the algebraic infinite tensor products, or finite or infinite tensor products of matrix algebra, and then that you get if you recover the supernatural number you get by looking at the abstract. You look at the abstract algebra and you can recover the supernatural number, okay? Either as K0 with the unit keeping track of the unit, or as just the trace values of the normalized trace, unique normalized trace on idempotent. And then in the free floating case, you don't get a concrete group unless you start with the particular with the matrix the matrix description, which you're not really allowed to. Okay, if you're classifying the algebras, but that'll give you one way of computing the K0 group. But you have to remember that that's not natural. You're only computing what the K0 group is what's natural, but that's not concrete. You're giving a concrete description of the K0 group. It's isomorphic. The K0 group is isomorphic to to the group that you get from the unit case that you started with. But it involves a choice of unit, which is, I mean, you don't, a priori, if you're just given the free floating algebra, you don't know whether to choose the unit for this algebra or for the 2 by 2 algebra, which would have twice the, it would be the number 2 rather than. Well, okay, well, that's, maybe we don't want to jump up and down on something so much that it squashes it, right? So I think there's on a given sitting, you should just look at something so much. Have we looked at this enough for the time being? Anyway, I would really suggest this. I mean, we're not assigning either homework or, I mean, either exercises or essays, but it was recommended the homework and well, things I'm suggesting in class recommended too. But, well, this is it's one exercise which could be a homework or it could be part of a more all-encompassing essay. All right, but that's the UHF algebra. Any questions? Well, that's, I always laugh a bit, talk a little bit when someone says, "Are there any questions?" Because if someone has to ask if there are questions, then there are probably questions. But that doesn't mean they're going to get them. Yes.
This is based on the homework question and you did give us K0
Yourself. I mean, what is the K0 group of a field? Yeah.
Yeah, and it's just the field itself. Right?
Well, yeah, but look, the reason that's a bit funny answer is if you with the K0 group is a group, right? And if we talk about a field, then there are two groups. There are two groups. We have to say which one.
We're talking about K0 of complex matrix and
Look, it's always the same for every field, okay? But that's one thing that's notable. If you look at K0 of a field, it's always the same. It's a certain group and it's always the same.
So does that apply if you take K0 K0?
Look, it just happens that K0 of a field is a ring, so you could take K0 of that. But I would say that in fact, if you look at the ring that you get from in the natural way from K0 of a field, I'm talking in circles now, but I think it makes sense, and Jared is making sense too. Except the question is a bit too. I'm not sure if it's the question he means to ask, but anyway, if you look at K0 of a field, it happens that in a natural way it's a ring, okay, and with unit. And if you take the K0 group of that ring, it turns out that you get the group that you get is the additive group of that ring. It happens. But that's already true for the given field. If you look at the, well, no, it's not. It's not. The given field has two groups. It has the additive group, and then it has the multiplicative group of non-zero elements. But in fact, neither of those is the right group, as it happens. So don't worry. So just think about it. Yeah, but also think of ordinary linear algebra, and the definition of K0, where you have finitely generated modules. Sorry? Well, okay, but yeah, but then now you're remembering what we've discussed, and that's so it's always the same semigroup, and so you're always going to get the same group, right? Okay, and one exercise was to go backwards. If you know that the K0 group of a field is what it is, just as a group, forget about the semigroup, then can you deduce what the semigroup must be? Which is the same as proving the basic facts of linear algebra, right? The dimension exists. Pretty elementary then. Yes, Evan?
I think I was like, I was a bit confused about that exercise because I thought it was a bit circular because it seems like we define the K0 to be the semi-group.
Yes, but yeah, well, sure. But once you do that, um, you don't, and you pass to the group. Once you have the semi-group, you can pass to the group. But suppose you throw away the semi-group and you're just left with the group. Then the question is, can you recover the semi-group?
More than one semi-group.
No, as it happens, there's only one. If you keep track of very elementary properties of this semi-group that follow from their trivial facts in linear algebra. Sorry?
So what about just like the positive even?
Well, I can't quite
Oh,
follow.
what about like just like all the even?
Well, look, when we say the K1 group is Z, we just mean, sorry, when we say the K0 group is Z, we just mean it's isomorphic to Z. Okay, good question, but then the exercise is this, and it's not that difficult. You just have to remember some trivial facts from linear algebra, and then you end up, if you can prove that the semi-group is the isomorphic to the positive integer, then that's the deep fact about linear algebra. Okay, you get that the dimension is well defined. Okay, so that's the exercise. But it's only a question of up to isomorphism. Good, but that's good to keep track of possible confusion. You know, half the time getting held up by something, an exercise or something, is just not doing all the chores ahead of time, expressing things, reviewing the expression of things, how things should be expressed in a clear way, removing the underbrush, if you like. Yes, Darren.
Follow up on that.
Yeah, but look, there was a guy, the late Reto Salinas, who was blind, and whenever someone said what you just said, he said, "What are you pointing at?"
Oh.
And I was looking in the opposite direction, right?
Pointing is also- Right, I
Well, look, we're not, don't stand on ceremony, but we should have, what I'm trying to say is clarity, okay? So what are you concerned about?
Just to follow up to the question. Does K0 possess transitivity? If you take it out, so
Okay, look, why, this is, I keep asking people to ask questions, okay? Raise questions, but sometimes maybe we could have a break with, can we have a break without questions for a little while? Okay, any questions? Okay. But by the way, I'm always free to be, I don't know how, well, today's Friday, no, it's not. It is, yeah, today's Friday. You can see I'm not a TGIF person. Maybe I'm TGIM, how about that? But there is a tutorial, and I'm sure that any question that I don't rise to, I think that Mr. Lau might be a little more sympathetic to have a little more time for. Because after all, he will have fewer people will fit in that room than will fit in this room. But doesn't have to be, since it doesn't have to be the same, since it probably isn't the same people every week. Everyone should think about attending for a while. I remember when I was the organizer of a Fields Institute program 30 years ago in Waterloo. It was one of the early programs in the Fields Institute. It was at Waterloo for the first year. We had a very we were very successful in getting visitors, okay? And even in spite of this is much difficult, almost as much difficulty then getting visas as now. And or financing people. So it was a slightly smaller place than here. So, but the director, John Chatham, now at University of Pittsburgh, chairman of the department, he once, much later when I was talking with him, he said, I was always very happy to approve your visitors, to see them come to the Fields Institute program, even if they had to lean out the window. For office space, for accommodation. Okay, but so the first interesting case where you want to talk about the functor and a classification functor, it's just a formality in the case of the UHF algebras themselves in the upper left-hand corner. But for the free-floating matrices, there's no natural concrete description of the K0 group. Okay, only up to isomorphism that it's a subgroup of the rational. It's what abstractly it's a torsion-free countable abelian group of rank 1. So it's called torsion-free rank 1, which means that it's isomorphic to some subgroup of the rational numbers. Okay, and using that and the fact that the isomorphisms in the unital case preserve the class of the unit, then you get you recover the supernatural number exactly. Okay, well, the exercise I'm suggesting is for the free-floating ones. If the K0 groups are just isomorphic as abelian group, then you have the two supernatural numbers n and n prime. What's the relationship going to be between them? Okay. Yeah, sorry, one is twice. Did you say? You're getting a concrete approach, which is very, very good. It needs to be corrected. Okay. I mean, I remember once Dijksma came to Queen's University when I was a master's student. He gave a beautiful lecture, but several times during the lecture he said something, and then he said, "Well, now I have to correct that. Say it a little more correctly." Okay. And that was his pedagogical device. So I appreciate your pedagogy. Okay? So the point is, you look at the arithmetic. Okay, you look at the supernatural numbers of arithmetic, and the arithmetic. You can't adding them is not natural, but multiplying by two supernatural numbers, or especially even including natural numbers, that's natural. Okay, and so suppose you, and by the way, it's almost you're 50% right, I would say. Okay, but anyone want to make a slightly more refined approximation? Yes, anyone? Well, okay, but you're not careful, you'll get the definition that they're equal. Okay, yeah, and so and don't forget, and I think it's a little too complicated. We've got two. Think of them as natural, think of them as just like natural numbers that you can add and multiply. Now, but so and also always go to special cases. Like if you have one of them, if you have one supernatural number, and then you multiply it by 2, that's the simplest thing you could do, right? The question is that going to give you the same free-floating algebra or a different one? Well, roughly speaking, obviously the same, because if you take 2 by 2 matrices over a free-floating algebra, it's the same thing, right? So that's a lightning. That's what I like to think of as a lightning computation. Why not just think about it? Let's leave it as an exercise, okay? If you have 2 supernatural numbers n and n prime, and the free floaters are equal. Free floaters are isomorphic. Then what does this imply? And of course, the way to decide what something implies is just go backwards. But what are some simple cases that do imply that the algebra is isomorphic. So check if you, well, just check exactly that if you take, by the way, one special case that where you'll get exactly the same thing is if you take 2 to the infinity and you multiply that by 2. That's too special, right? But obviously, since the number is the same, you're going to get the same algebra, even before you do the free floating. The unital ones, I mean, 2 to the infinity, 2 to the infinity, they give you the same unital UHF algebra. So that's not even a good joke, right? If I can't find a joke, it's time to go on to the next item. Um, um, the free floaters are the first case where you have classification functors really coming into their own, okay? But what's the next case? The next is general AF algebra. Look at general AF algebras, then you still have K0, right? And they have the semigroup. In fact, you don't need the group, just look at the semigroup, Eulian semigroup, or consider its image inside the group. Consider the group together with the image of the semigroup, and that gives you what's called an order group. Well, turns out that the order group K0 for an AF algebra. What's an AF algebra? Well, UHF was a limit of single full matrix algebras, right? You take the finite, you take more and more. Where do they go? Did I erase them? Oh no, what happened to the? Oh, here. Oh, yeah. Couldn't see choose an angle. All right. There's the first one. Second one. That's a single matrix algebra, right? Tensor of 2 others. Keep on going. Except that if this is infinite, then it's already limit. But if you take the finite matrix algebras, then that's called the UHF algebra. But then the AF algebras, where instead of a single full matrix algebra, you look at just the arbitrary finite direct sum of full matrix algebras. Okay, you have maps, and you look at the algebraic. Sometimes we'll look at the algebraic limit as an algebra, and those can be classified again just by K0. That's K0 is a classification functor for these so-called AF algebras. So UHF and A. Okay, so it's in the book. It's in the book. But maybe you could try working it out anyway. When I was doing it, which was how long ago was it? Anyone want to guess? It's exactly 50 years. Okay. When I was doing it, it took me a while. For one thing, I was older than you people already. And you always slow down, I guess. Okay, you can tell, right? All right, but I should be finished by now. Okay, maybe, but but if something has already been done, if you know it's been done, then that's supposed to help. That's believed to help. Well, there's one way in which it might not help, right? One way in which it might help to know hasn't been done. If you know it hasn't been done, then it's a prize, right? Whereas if you know it has been done, then you might just shrug it off. Well, anyone can do it, and maybe no need to spend my time on that. Well, it's a question of how much you like assigning exercises to yourself. Okay, well, I recommend it as an exercise. You can peek in the book after a while, see what gets done. but the cat is already out of the bag. It's the ordered K0 group, okay? Now you have to know why it works for AF and not for an arbitrary C-star algebra. It works more generally in AF, but then you have to combine it with K1, okay? Which we haven't even talked about too much yet. I can tell you what K1 is very simply. You take the suspension of an algebra, the Banach algebra, and take K0, okay? And that's K1. Suspension, what's the suspension of a Banach algebra? Well, you take the real line, look at functions from the real line into your Banach algebra. Banach algebra is B for Banach. Banach spaces were invented also by Banach. I guess he didn't invent Banach algebra. But of course, Banach didn't call them Banach spaces. I say, of course. What do you suppose he called them? I wish no. This is his life was ended tragically, I believe. But okay, but I won't be. Shall I say it? Okay, it's meant as an admiring comment. Okay, he called them B spaces. So here's B. And look at B-valued functions on the real line, which vanish at infinity. They get arbitrarily small in norm if you go out. And the norm is the sup norm, okay? You take the sup norm. And that's point-wise multiplication and addition and multiplying by scalars. That's a Banach algebra called the suspension of B, written S of B. And for any complex Banach algebra, any real or complex Banach algebra, K0 of SB is by definition, that's K1 of B, okay? And what do you suppose K2 of B is? Well, it's K1 of S of B. But what do you suppose it is? What do you suppose if we talk about complex Banach algebra? So what do you suppose that K2 of B is? Who said that? Yeah. Okay. You've been peeking. Either that or you don't need to take this course. Okay, good. Yeah, okay. Good. But that's maybe we should be talking more about that. That's what you might say is it's in terms of overall K theory. That's almost the be all and the end all of the course. Okay. Well, it's you know what it's called? Yeah. And so that's a grade A theorem, okay? Fully in terms, and it's sort of a general theorem. It's not. You don't need to know. You don't need to know what a C-star algebra is. It's just true for a Banach algebra. And in fact, to prove it for a C-star algebra, which is done in the textbook, you have to prove that the K0 group of a C-star algebra is the K0 group of a Banach algebra, of it considered as the Banach algebra. Because Banach algebra doesn't have has idempotent, but it doesn't have star operation, right? And for C-star algebras, the whole setup for K0 is defined is expressed in terms of self-adjoint idempotent. Now this is a minor thing, but okay, but it's and C-star algebras are I think it's better to give a course on C-star algebras rather than Banach algebra. Because for one thing, the this C-square algebra theory, the case of amenable Phenomenon algebra and amenable C-square algebra, what happened? The separable case of complete classification, existence of a classification function in both settings. These are considered major theorems nowadays. Just like in group theory, you have the classification of finite simple groups, right? This is probably this is well, it's still being checked, but in fact, just the fact that it's still being checked means, I guess, people think it's important. You might you might look up the look up on Amazon sometime. See if you can order the see if it's possible to order the atlas of finite simple groups. So it would probably it would say what it costs and how long it would take to deliver, and you might get some reviews, right? It's interesting to see a review of the atlas of finite simple groups. Well, okay, so the question is what is special about AF algebras for more general C-square algebras, like if it's a T algebra, say simple AT algebras, where T is a circle, okay? So instead of points, you have little circles, okay? And that means you look at matrix algebras, matrix valued functions on the circle, okay? And so if you look at the look at AT algebras, and there's no nice classification of them in general, as like there is for AF algebras. But if you take simple ones, then there is a nice classification. No non-trivial two-sided ideals, and and that requires K1. And but there's a discrete number of steps. Just one. If you add one more invariant, then with the tracial simplex of states which are traces, you keep track of that, and a natural pairing with K0, then you do get a classification theorem for general class of algebra. And you might ask, is there an atlas of classifiable simple C-square algebra? Well, the reason there isn't is that with the finite simple groups, you can just number them. Number one, finite simple group number one, finite simple group number two, and so on. The sequence that has just checked that you've got all of them there and none of them are repeated. And then you publish that in the big book. With the C-square algebras, UHF ones are parameterized by a Cantor middle third set, okay? And that's the isomorphism classification too. But if you tensor them, that's an exercise. If you tensor them with if you look at the free floating UHF algebras, then we don't know what the isomorphism classes are parameterized by, because that's still an exercise. It's still a gleam in people's eye. Okay. So I hope to see people coming up with the answer. And we've agreed, I hope you've agreed, we've agreed you multiply a supernatural number by 2, you're going to get the same free floating algebra. And actually the general answer is just piled a little higher and deeper, right? Okay. And maybe that's, okay, well, let's move into the second half of the afternoon. Some questions, maybe. Yeah, I'll be glad to try if I can answer a question. And I'm sure Mr. Lau will room 6180.